in the industry. Now today that talk will be the basis, the working basis for all 3GPP based talks throughout the week. So I know it's late in the afternoon, I know some of you are jet lagged, but I think it's worth paying attention because a lot of things which will come up here will be very useful later on during that week. Thank you very much. The floor is all yours.
Thank you, Misha, and again thanks for the invitation, and I really appreciate to be here. First time in Barcelona actually, so unfortunately I have to leave tomorrow, but nevertheless I will try to enjoy as much as possible. Switch on the mic. I think it's already. Oh, yeah. It's on, yeah. Can you hear me? Yeah. Okay. So basically I got the task to talk about 3GPP LTE Evolved Packet System and what it is in general. So the Evolved Packet System is a very huge and large, let's say, thing, if you want so. And I try to cover the most important aspects of the EPS, which is basically the core network, the quality of service architecture, and also, of course, a little bit on the radio access side. Also, I will not go into too much detail here because I saw that tomorrow there is Willem Mulder from MIMO On, who's really an expert on this topic. So I think he will also give a nice overview about this topic there. So, and again, also because we are talking about femtocells, I had to insert this small sub-sentence here, GPP Evolved Packet System, and what has it to do with femtocells? This will also, let's say, one of the topics I will address here. Let's go on. So, that's the outline of my talk. So first I would like to talk a little bit about where does 3GPP EPS come from, where does LTE come from. So I will give a short overview about the, if you want so, history of cellular mobile networks starting from UMTS. So not so far away, if you want so. And also about the motivation of why is this happening, why did this, is this development started. Then I will give an overview about the Evolved Packet System architecture, including the QoS architecture, the different functional entities which are defined by 3GPP, and also about the, let's say, a little bit about other access systems or other radio access technologies than 3GPP, which are also possible to be integrated into EPS. Then I give an overview about Evolved UTRAN. So E-UTRAN, you see it here. Well, that's basically the radio access side. And UTRAN means, E is always evolved in this context. UTRAN means UMTS, Terrestrial Radio Access Network. So that's basically everything which has to do with base stations, and in the old UMTS times also with the RNC. And then I will talk a little bit about femtocells and what's the specific 3GPP approach to femtocells, because that's a little bit different to the, let's say, often commonly perceived idea of femtocells just as small cells. That's a little bit more here. And if I have time, I will give a very brief outlook on LTE-Advanced and currently hot topics, which are expected to become important over the next few years. So first of all, I would like to give an overview of what the progression of cellular peak data rates looks like. If you see here, we start with a good old GSM system, which all of you use most probably. We have data rates about 9.8 kilobit per second. And over the year, we have a nearly 10-fold increase every 5 years towards very high data rates, which are currently the peak data rates, which are currently envisioned, are in the range of 1 gigabit per second. So this is basically a requirement which came from the ITUR, which defined an IMT advanced program. And in this program, they said, we want to have the next generation mobile network, basically 4G, if you want so, or beyond 4G. And this mobile network should support peak data rates of up to 1 gigabit per second. You can also see that there was quite a large time between GSM and GPRS. GPRS was basically the first really packet-based radio system. So it's a time of approximately up to close to 10 years. And after the success of GPRS, the development really started to take off. So first we had EDGE, which is basically an enhancement of GPRS. Then we had UMTS with promised peak data rate up to 2 megabit per second. We all know that that didn't happen so much. It was more around, let's say, 384 kilobit per second. Then we went to HSDPA in 2005. So this was the first time we really had an, let's say, a transition from the circuit switched approach, which was basically the principal foundation of GSM and also from UMTS, to a packet switch approach. So circuit switch basically means that you reserve an, let's say, an end-to-end circuit between users or between participant in a communication. And that's also where the term operator comes from, yes? So an operator was somebody who actually plugged, let's say, different lines to different end-to-end connections. And it took a long time for the operators to come away from this paradigm and to reach the packet-switched paradigm, which means you are transporting packets, like in the internet, and are routing them or scheduling them if you need it. Then WiMAX came in 2006, I would say, in a first deployment, and this was a little bit shocking for the 3GPP people, because they could see, well, we have a new air interface, and WiMAX was a system which was at this time quite ahead of the capabilities of 3GPP systems. So this also gave 3GPP kind of an extra kick to develop HSPA plus, and then finally LTE. And I'm saying this because my background is actually from WiMAX, so I'm a WiMAX guy. I went there for 3 years basically, and I think it has a lot of positive influence also on the 3GPP side. And finally, we have here WiMAX 2.0, so IR2.16M, and LTE-Advanced. And of course, this, let's say, graph is a little bit misleading, because peak data rates, as you may know, they are, first of all, only reached in laboratory environments. And second, there's a comparison not very fair, because with the increasement of the data rates, also the use spectrum increased hugely. And especially to reach this 1 gigabit per second, ITUR said you can use 100 megahertz of bandwidth, so of spectrum bandwidth, basically. Yes?
Theoretical analysis, or just a demonstration, actual demonstration in laboratory?
No, this is peak data rates. If you take a specification and assume all the best, basically, then you get these data rates.
But I'm wondering, with 100 megahertz, if it's LTE has to achieve 1 gigahertz, then it means it will rely on higher modulation than 64 QAM.
No. What will be done is actually
MIMO?
Yes, a little bit MIMO, of course, but the most important aspect is spectrum. So what they do carrier aggregation. They take different parts of, maybe even scattered across the spectrum, and all serve it at the same time. And by this means you can reach 100 megahertz.
Yeah, okay, including that carrier aggregation, because in LTE we have around 20 megahertz.
Yes,
LTE maximum, and LTE with carrier aggregation will have 100 megahertz.
Yeah, maximum.
So if we want to reach 1 gigahertz, it means we need to transmit 10 bits.
Yes.
So, but 64 QAM gives us 6 bits.
Yeah, plus
with no coding, and with coding it even less than that, and with signaling even less than that.
Yes, I agree. So what has been done, the LTE-Advanced standard and also 16M standard has been, let's say, designed in a specific way with spatial multiplexing with 8 antennas and all that stuff, that you can, in theory, reach this 1 gigabit per second.
Yeah,
that's basically. I'm not saying that it will ever happen, but in theory, it's possible. Well, and of course, what you also need are smaller cells, femtocells. You need to increase the spatial reuse in order to have, let's say, the number of users which share the same spectrum should be reduced. So what are the main drivers and the main motivations here? That's kind of on, let's say, motivations from user perspective, from business perspective. And maybe this citation is quite interesting. That's basically the start of LTE. That's defined in this technical report. You see here, 22.987. That was a report on feasibility of a long-term evolution. I don't know the exact name. And there seems to be a common understanding in the mobile communications industry that the technical and commercial evolution of this industry sector points towards an AIPN. So AIPN is an all-IP network. So that was basically the main driver behind this. And all-IP network implies also that all the internet applications should, will be transported above on top of cellular networks. And of course, you have the typical, let's say, drivers like you need high-speed mobile access, diverse mobile network services, seamless services, experience across access technologies, and so on. So if you just think of Siri, who of you has an iPhone 4S? Nobody? So iPhone 4S actually, the Siri application, every time you use it, it sends a request to the Apple server and processes the data there and sends the request back to your iPhone, which then basically interprets it correctly. This has a huge impact on the, let's say, bandwidth requirements of mobile services. This means that every time, or at any time, there can be a new development, a new innovation coming from this huge internet innovation pool, if you want so, which increases the demand for bandwidth drastically. And that can be sometimes also a problem. So I'm not sure if you're aware, but there was recently some news about an operator, a large operator, which basically had to shut down or experienced some outages in the network because of Android systems, basically, because they are sending permanently some kind of signaling data. And, well, there is, let's say, put it like this, there's always need for more bandwidth and always need for more optimizations into this area. Well, other drivers from a business perspective, of course, large volumes of IP traffic in a cost-effective manner, which means operators want to charge for this large volumes of IP traffic and kind of new, let's say, services, user-to-user, user-to-multicast traffic over IP. Non-CGP access technologies with minimum impact refers to basically to Wi-Fi and also to a lesser extent now also to WiMAX, which is perceived as being, let's say, more cost efficient for deployment more often. Interworking with other networks, but considering mobility, security, charging, and QS. Charging is a very important point here. QS, of course, too. And a control fixed mobile convergence issues, okay. Then from a technology perspective, well, always good, higher data rates to end users, multiple radio access system. And I also would say that there was also a, let's say, drive coming from competing standards. So this refers to 3GPP, this slides here. So mobile WiMAX challenged market and technology leadership of 3GPP systems, so they basically had to react and develop a new system which is, let's say, competitive to mobile WiMAX. So this is another overview which shows the radio technologies which have been in use over the time. Also quite interesting because what you can see is that there is a convergence of different radio technologies towards OFDMA. I think most of you guys are probably coming from the physical layer perspective. You all know what OFDMA is, I assume strongly. And you can see here it all started either with GSM or with IS-95. This was a CDMA system in the United States, or it's still active. And so GSM, GPRS, Edge used TDMA, FDMA multiple access. IS-95 uses CDMA and wideband CDMA, also UMTS uses wideband CDMA. Then the evolution went to HSPA, so HSPA is high-speed packet access, which basically was an, let's say, a successful attempt to packetize the UMTS system, which is, as I said before, still in the circuit-switched paradigm. And then OFDMA come into the play, and we started with fixed WiMAX, mobile WiMAX, and then finally LTE release 8, which then will be developed, or is developed already, partially in LTE release 10, which is LTE-Advanced, by the way, according to 3GPP. And I would more say LTE-Advanced are releases beyond release 10, because there the real new stuff will come. So why actually is OFDMA the let's say multiple access or technology of choice today? There are 5 reasons. The first is, you know this, it's robust in multipath environments. What more interesting is that you have a possibility to do a flexible spectrum allocation simply by adjusting the number of OFDMA carriers. If you think of other technologies, that's not so simple, cannot be done so simple. In, for example, a wideband CDMA, there you have always 5 megahertz bandwidth, and you cannot adjust it simply by removing a few subcarriers there, and you can then use it in another band. This is a large, let's say, advantage of OFDMA over other technologies. Receiver hardware is now, there are now efficient implementations of receiver hardware. MIMO can be done nicely in frequency domain. So it's also not so simple. I'm not an expert, but it's also not so simple to be achieved in CDMA systems. And of course, you can nicely utilize the frequency diversity gain. If you, you all know this, of course, if you have a wideband radio channel. Yeah.
Is there somebody still interested in WiMAX too?
Yes.
For example, among the key players?
Let's say there are some companies which are still, large companies which are still interested in WiMAX 2, and they will develop it.
As a competition to LTE?
I would not say it's really a competition. It's more, let's say, so there are operators which have deployed WiMAX networks,
okay.
yes? And it's about migrating or evolution of these networks towards higher data rates.
Okay.
And you have 2 possibilities. Either you can completely build up a new LTE system, which means you don't have any data service until this time, or you can enhance the current system, and maybe you can also build in parallel up an LTE system.
Okay, and where does 802.16J fit? Means,
J? Yeah, well, J was an enhancement for
relay station.
For relays, yes.
And
M?
So how does M differentiate from E?
So so J is basically an enhancement of 16E.
Okay, yeah.
So yes.
For relays, yeah.
For relays, yes.
And this M is for, means how does it differentiate from E?
M was originally supposed to be just an let's say enhancement of 16E. So by taking certain part of 16E and increasing it, improving it a little bit, but in the end it was a completely new standard. So it was just recently approved to be a completely new standard, which stands on its own basically.
And it supports relays?
It supports relays, yes.
So there's no need for J?
No, at least not for. I wouldn't say that, but at least not in 16M systems.
Yeah, I was just going to say that 16M absorbed J and enhanced it actually.
Okay.
So
yeah.
So you don't need J7.
And also supports femtocells, by the way. Okay. So now, after talking about that, I would like to give maybe an overview what is 3GPP in the end, because there are so many. So 3GPP is often referred to as kind of institution which builds or creates all these standards, and maybe it's interesting to know what they are actually doing, what they are consisting of. So they were founded in 1998 by different standardization organizations, so national standardization organization like ARIBE, that's Japanese, ETSI, you know it, that's the European Telecommunication Standardization Institute. Then T1 work group from ATIS, this is from the US. TTA, that's Korean. And TTC, that's again Japanese. Don't ask me what's the difference between both. And now we also have the CCSA, that's from the basically the Chinese standardization organization. So these national standardization organizations basically form the body which forms CGPP. And CGPP gives if CGPP releases a standard, it will be transformed into a national standard after this. So, for example, if you go to the ARIBE website, you can see the exact same documents which were also provided by CGPP on their website, just that it's called ARIBE now. Yes? And they have market relationships to many other interest organizations, such as Femto Forum, GSMA, UMTS Forum, and so on. And the scope was originally to specify a 3G system, that's therefore the name, Third Generation Partnership Project, which basically in the end resulted in UMTS. So UMTS, Universal Mobile Telecommunication System, talked about this before, it's basically based on wideband CDMA. But today it's responsible for all, so it basically inherited all the communication standards from ETSI. So this includes GSM, GPRS, and Edge. So it's responsible for maintenance of these systems. Also for UMTS and E-UTRAN, so the radio access network part of it. So there are still some developments going on in HSPA. And of course, all the development of the evolved U-TRAN, which this is basically LTE. Yes? So LTE is evolved U-TRAN and CGP core network evolution, or maybe a better term would be system architecture evolution. And now it's also written in some of the documents there, CGP considers a long-term evolution. So that's basically the long-term evolution is not only a certain release, so it's the whole, let's say, process of improving the CGPP technology.
Sorry, Andreas, just one question. Can you go one slide back, please?
Yeah.
So all these organizational partners funded 3GPP, okay? Yes. So they are part of 3GPP, right?
Yeah.
So in 3GPP they develop technical documentation but this documentation is not a standard, right?
It's not an official standard because 3GPP has not the legal power to define it as this, if you want so.
Okay, so this documentation is used by the organizational partners to publish the standards, right?
At least that's my understanding, yeah.
Okay, and related to that, besides the 3GPP documentation, these partners, on their own, they also develop technical documentation, right?
So, for example, ARIBE takes the 3GPP documentation, approves this, if you want so, and makes their own stamp on it. That's now an ARIBE 3G system, but it's basically the same.
Yeah, no, but my question was more related to the fact that, for example, ETSI, the partners of ETSI also develop technical documentation different to that of 3GPP,
of course,
but then they publish the 3GPP documentation as a standard.
Yes.
So they are just creating different standards at the same time?
Yes, I mean, ETSI, for example, has a much broader scope than 3GPP. They develop also, let's say, vehicular communication technologies and probably much more.
Yeah. Okay, thank you.
Well, so 3GPP standard releases, so stable release, so what is a release? A release is something, a stable release across all documents of all specification groups, if you want so. So there's a freezing date, and after this freezing date, there will be no new major features come into this release. For example, if now release 11 hopefully defines carrier aggregation, then this should be finished. There will not be something major new features into this release. And we have an overview of some major 3GP releases. So starting from release 99, release 4, release 5, very important one because this is HSDPA. All of you use. Release 6 introduced in the enhanced uplink. Now HSDPA became HSPA, which is high-speed packet access. So HSDPA is high-speed downlink packet access. Then release 7, improvements for HSPA plus. Yes, you get some higher data rate there. IMS is the IP multimedia system, which is basically used as a, let's say, platform for any kind of voice call set up in LTE, or not only voice, there are many different kind of multimedia applications there, but this is one of the main applications. Then release 8 is the evolved packet system. Release 9, further improvements, and release 10 is basically LTE-Advanced. Of course, there will be more releases. Release 11 is currently in development. Freezing date, I think, is end of 2012. And release 12 is already, let's say, started. There are already some work items which are under discussion there. So I had also the idea to show you some, let's say, idea what's all going on in the different specification groups, but I think we should maybe speed a little bit up. So TSG GRAN, so this is technical specification group, is TSG. GRAN is the GSM Edge Radio Access Network, so the old legacy network, basically, GSM. This is still active here. Maintenance and development of all aspects regarding radio here. Then we have the RAN specification group, so everything which is going on in the user equipment and in the base station and also in the RNC for UMTS regarding radio transmissions, basically. MAC-PHY is done here. Then we have the system architecture group, which basically defines the evolved packet core and also the services, the service architecture, including the quality of service architecture. And then we have the core network and terminals group, which is responsible for stuff like IMS and SIM card specifications and, let's say, core network interfaces, protocols, and all these aspects which are quite scary. I don't want to go into detail here. So I don't know how familiar you are with this website, but if you press on the CGP website on the specification button and then on specification numbering button, you come to this page, basically, just looking a little bit nicer. And this gives you an overview of all the different, let's say, documents which are grouped into series starting with different numbers. And I try to highlight some of the more important ones. If you are looking for something, a certain aspect, for example, like how is evolved packet core defined? What are the important documents here? You can, for example, go here to this technical realization subject. So that's the 23 series. And here you find some important specifications regarding the EPC, which is 23.401. Okay, don't want to go into detail here, but you will find that everything related to service architecture and to the core network you can find in this specification group. Then we have radio aspects. So this is only for UMTS. So there's nothing about LTE in this series here. And then, of course, we have here LTE and LTE-Advanced radio technology. That's the 36 series. So there you will find everything related to MAC and PHY of LTE or evolved UTRAN. And especially here, this document, 36300, that's the overall description document. And I'm sure that most of you have read it completely. Yes. And we also have here 37, that's quite new. Here we have some for example, mobility enhancement for home eNodeB. That's a technical study item there.
Question: what is the whole process of standardization? Once the 3GPP freezes are released,
Yes.
it becomes a liability on operators. Sorry. Once 3GPP freezes are released, it becomes a liability on operators to implement those features in their products, or no? It has to be standardized. Even after standardization means.
Well, there are always some core parts which have to be implemented and optional parts which are must
Proprietary,
not, not proprietary. They are standardized, but there's not necessarily a need to implement them. So,
and the standardization is local to each country, or it means, for example, for LTE.
well, okay, maybe I should. So the standard is defined de facto by CGP, but it will become a legal standardization document from the national standardization entities. At least that's my understanding.
Okay. But like multinational companies, for example, NEC has launched a base station, LTE base station, back in 2010.
Yeah.
Which contained load balancing feature.
Yeah.
But load balancing was not there in release 9, neither it was there in release 8.
Yes.
It came into being in release 10.
Yeah.
But by that time, release 10 came into after the product was already launched.
Yes.
So how did it work? Means they launched the product before
Of course.
the release was frozen?
Yeah, this can also happen, yeah.
So they took the risk?
Yeah, yes, always the risk that you implement some pre-standard product, which then may lead to some problems later. If there are significant, let's say, differences in the standard itself after the release, yeah.
Or they have some kind of hidden insight into the standard before it's made public? Means because they're members of.
Well, of course, you can then try during the standardization process to influence the standardization group to, let's say, not implement certain changes. That's always
So it's
the goal of
political.
Yes. Okay, so now we come to the real thing. Overview of the Evolved Packet System architecture. So first of all, maybe what's EPS, Evolved Packet System? The Evolved Packet System is both the Evolved Packet Core and the Evolved E-UTRAN, so Evolved Radio Access Network, if you want so. So if we talk of EPS, we mean the whole, let's say, system which you can see in terms of a mobile phone or something, and all the network which is located in the mobile operator, and is also standardized. So EPS designed to be a purely packet switch system. It is quite new in comparison to the let's say UMTS core, which was implemented before, which means basically that the IP multimedia subsystem, so IMS, is targeted as a voice service platform. So if you want to make a voice call, then you will basically send session initiation protocol messages towards the mobile network, and this is then processed correspondingly. So the EPS is similar to the GPRS core, but it's more flat. So one of the nodes in the user plane have been removed, but the general the GPRS tunneling protocol remains the main protocol for CGP accesses, which basically means that all data, I can show it in the next slide maybe, all data which is sent between different nodes in the EPS is tunneled with this protocol here. And this protocol, GPRS tunneling protocol, is standardized also by 3GPP. And also the EPS enables, so this was one of the major design goals originally, EPS also enables the interworking with non-3GPP accesses. For example, Wi-Fi, of course, WiMAX, and CMA 2000. And there are various options for mobility between different CGP access and non-CGP access, and one is also based on either on proxy mobile IP or on dual stack mobile IP. Oh, what was this? Better. So let's have a look at the, let's say, basic architecture of an EPS system. So on the very left side, you have the user equipment, which is basically the mobile phone. Then you have here an interface called LTE UU. Then here's E-UTRAN. These are basically base stations, eNodeBs in that case. And then you have various, let's say, functional entities in the core network. I think I also have a nice animation here. So on the other side of the, let's say, of the whole mobile network is the PDN gateway, the Packet Data Network Gateway. So that's basically the point where all the data is entering, so all the data is leaving the mobile operator network. Yes? So this is happening in the PDN data gateway, which also implies if you are downloading, for example, a web page somewhere, maybe here, here should also be the internet, then all the data has to go here through to all these nodes until it arrives at the UE, and also the other way around. Also, it's responsible for IP address allocation, and also it's responsible for charging, basically, at least, yeah. And it enforces also quality of service. Important point, we'll see it later. So the second is a serving gateway. So that's the serving gateway is a mobility anchor. So if you move from one eNodeB to the another eNodeB, then the GTP tunnels, which are existing here between the E-UTRAN, between the eNodeBs, and the serving gateway, they are switched from one eNodeB to the next one. Yes? So therefore, this is a mobility anchor. Then we have the MME, the mobility management entity. And this is, as the name already says, responsible for everything related to mobility in terms of management. For example, for mobility in idle mode, so where you are going to from one eNodeB to the next one, and the UE has to send periodically some location update information so that the MME knows then where the UE currently is, yes, in which coverage area from which eNodeB the UE is located. Paging means that if an incoming call tries to basically connect to your UE, the MME is responsible for finding this user equipment then. Authentication, bearer management, etc. And as next one, we have the PCRF. That's the policy, control, and rules function, which basically is about providing policies for quality of service enforcement. So, for example, if it finds out that you are using Skype somehow, then the operator could try to give them a better quality of service than comparison to just an example. And of course, we also have roaming between different operators. Therefore, we have here the example with a visited public land mobile network. So this is visited public land mobile network and the home public land mobile network. And basically what happens then is that, at least in this basic configuration, is that all data is routed from the visited network to the home network, and then there it exits the mobile network into the internet, which is quite inefficient if you think about it. Then you also have, of course, a legacy radio access. In this case, we have the GRAN, so GSM, GPRS, and we have the UTRAN, so UMTS radio access. And here we have the SGSN, the serving GPRS support node. And they also need to know some information on regarding mobility, because as you remember, we want to support handovers between different kinds of radio access technologies. So all this together is a 3GPP access, yes? But we had the, let's say, approach not only to support 3GPP, but also support other radio access technologies. And therefore, we need to enhance the architecture even more. And in this case, so we still have the most important nodes here. I forgot to mention here the HSS, it's the home subscriber server. it's basically a database where all your data related to, let's say, to your subscription. So, for example, your telephone number, your email, so your unique identification of the SIM card, and so on is stored. Well, what happens then here that we have different kind of access types. For example, you have trusted non-3GPP access. This would, for example, be WiMAX with a SIM card. There are also some other criteria which have to be fulfilled in order to be a trusted non-3GPP access. And you see here then it's connected via this interface to the PDN gateway. So this is the entry point basically for non-3GPP access. So could say it's not so trusted. And of course you also have non-trusted CGP access. And in this case you have also additional here on let's say security gateway, EPG, which kind of filters out everything which should not go into the direction of the mobile operator. And you have also a CGP AAA server which takes care of everything related to authentication and accounting and stuff like this. That's basically connected to everything. So this is one possibility to also connect non-CGP access like Wi-Fi to the CGP core, but there are many more. So if you're really interested into this, there is an overview of this into one of the specifications. I also name it at the end of the document of this presentation. And I think you have 6 or more different kind of configurations how you can achieve this. But the key point is that EPC or EPS is able to do interworking between different radio access technologies. Okay. So this was one part. Another important aspect is quality of service. So mobile operators want to, let's say, guarantee some quality of service for different, for their users, yes. And for this purpose, the 3GPP defined the bearer concept, which basically means it's like an end-to-end virtual, tunnel, if you want so, which certain QoS properties, for example, bandwidth and maximum packet loss and something like this. And these bearers here are, so the most important one is the EPS bearer, which exists between the user equipment and the packet gateway. And the quality of service profiles, basically, they apply to this EPS bearer. So on this link here between these two entities, there must, for example, not be more higher packet loss than 10 to the power of minus 6. And then you have some sub-bearers, if you want, so between different other network entities, like, for example, radio bearer, very important, between UE and eNodeB, and on top you have the ERAP, and so on. What also should be mentioned is that there's a one-to-one mapping between the bearer, between the EPS bearer and the radio bearer. So you cannot have something like, I have one EPS bearer and many different radio bearers to do some, let's say, traffic differentiation on this. This is explicitly forbidden in the standard. And what's happening is actually that traffic is coming in here from the packet gateway, and here it is mapped by means of traffic flow templates to different kind of bearers. Yes? So why is this important? Because the whole quality of service concept is enforced at the granularity of EPS bearers. And there are two different kind of EPS bearers, if you want so. First of all, there's also always a default radio bearer. So as soon as you switch on your mobile phone and connect to the network, you get a default radio bearer out. So I do the same mistake also. So you get a default bearer. And all traffic is mapped in the beginning to this bearer. And so all this traffic also has the same quality of service treatment, if you want so. Yes? But then there's also the possibility to set up dedicated bearers for certain type of traffic. A good example, for example, is voice traffic. Voice traffic needs other quality of service parameters than internet traffic, obviously. And in this case, in this way, you have a differentiation of different service classes, which actually works fine in theory, but has some drawbacks. I will come to this later. So what is an EPS bearer QoS profile? It consists of, let's say, of a triple of parameters. One is QCI. That's the QoS class indicator, which basically points to a further granular definition of QoS parameters. Then you have the ARP, allocation retention priority, which gives you an indication of how important this kind of traffic is. This is important for admission control in the eNodeB. So the eNodeB basically then decides, because of this value, I can, for example, kick out one user but leave the other in. Yes. And then we have the guaranteed bit rate for a certain type of bearers, for example, like voice. This means that this bearer also always has to get this data rate. So how is it done? So the important thing is that packet classification is done in the, let's say, in the PDN gateway. And there it can be done by different means. Packet classification means that each packet has to be inspected, whether it belongs to a certain traffic class or not. And you can think of it, it's quite complex, yes? So if you have, let's say, you have huge amounts of different kinds of internet applications and or protocols, and all use different kind of, let's say, have different packet profiles. So if you want to find out which traffic belongs to which, let's say, service flow, then you have to do it in the packet data network gateway, and this can be quite, let's say, demanding computationally. So you can do this by means of IP5 tuples or by means of DPI, which is, of course, even more demanding. But at least this is the idea behind all this QoS concept. And the eNodeB then just takes the QoS profile and maps it to certain parameters. So but there's another aspect here. It's on the in the packet data network gateway. There's the policy and charging control, the PCC function. The PCC function basically enforces QoS policies on bearers. Yes. So all this thing here is the policy to the PCC, and the most important part here is the PCRF, which we already saw before, and the PCEF. The PCEF is the policy and charging enforcement function. So this function here in the gateway actually marks basically packets as belonging to one certain bearer. And the PCRF gives the PCEF the rules how to do this. Yes?
Diagnosis of class of packet has to be done at each router, or just once at one node in the architecture?
At one node, at the PDN gateway. Because then it's tunneled in the entire GTP tunnel, and then it has a unique identity basically. So then the system knows that it belongs to this bearer. Yeah.
For each class, there will be a tunnel.
For each class and for each service flow basically. Well, it depends. For each marked service flow. So some default quality of service classes. I think you probably have seen it. So there are 9 predefined quality of service classes, and they are again grouped into guaranteed bitrate classes and non-guaranteed bitrate classes with different RP priorities. You see it here. And the only parameters which are defined here are a packet delay budget, end-to-end, between UE and PCF, just to remember. So not between UE and eNodeB. And also packet error loss rate, also again end-to-end, not between UE and eNodeB. And these different classes are then mapped to different example services. But you are free, or operators are free actually to define more QCI classes, yes? So it's only an example for default QCI classes, which are always implemented, but you can do more. So what's important is here that this QCI QoS parameters, they must be mapped to scheduling or radio resource management parameters in the eNodeB. For example, if you have a nice scheduler, you have to take this packet error rate and packet delay budgets, have to transform it to take into account of the rest of the network, basically, and then adapt the parameters for it. Also hybrid IQ and RQ. So in theory, this is how quality of service and policy control works. So again, maybe to show it a little bit more, let's say, yeah, in a nicer way. So the ideal case is that you have the internet with its various applications, like, for example, the always use Skype as an example, or video, or you have some nice cloud solutions and stuff like this, whatever you can think of. Then this traffic comes to the PCC, co-located with the packet gateway, and the PCC maps this internet traffic to EPS bearers. So in the best case, to dedicated EPS bearers. For example, then you have an extra dedicated bearer for Skype. You have one extra bearer for video with a certain guaranteed bit rate. In the end, all this traffic is transported on its dedicated bearer to the eNodeB. The eNodeB knows the quality of service parameters and is able to map it perfectly on the radio interface that they have perfect quality of experience here on the user equipment side. That's how it normally works, or no, ideally works. In theory, in the reality today looks different. The reality today is that all internet traffic is mapped to the default bearer, and all traffic is treated the same way, and yeah, you have no guarantee actually for your quality of experience or quality of service in the UE. At least that's my understanding of how it's implemented today. So it's not so good, and I think there's a lot of room for improvements and for further research to make this better. Okay. So how in time? So this was basically an overview of an evolved packet system, at least the aspect which I selected for this. Are there any questions on this part regarding some functionality which you are not?
I'm wondering about the whole tunneling procedure. I mean, aren't we doing a little overkill of the whole system? How much do we really need it? Or is it just an artifact of our radio access network priority classes, or we have something to map to?
Oh.
Because if I think we talked about Wi-Fi maybe even being able now to do all the mobility, etc., it means it will be flat until the access point.
Oh, no, okay. But, so you need for two things. The first thing is actually mobility. Because you remember the serving gateway is the mobility anchor. I should have shown this. So if you move from one eNodeB to the next one, the serving gateway will switch the tunnels from one eNodeB to the next. Yes? And if you have you can also have a handover between serving gateways, then it completely switches the whole, let's say, handovers the whole tunnel to this. So that's the first reason why you need it.
Well, it turns out that Wi-Fi is working on a way that you get around that. We don't know whether it will work. I don't know, but this is what I understood. If it works, it means the whole bearer thingy for the handover, well, it's complicating life.
Okay, I'm not sure about this Wi-Fi hotspot tool, but as far as I understood, it's more an enabling technology to enable a fast recognition of or scanning of co-located of neighboring Wi-Fi access points, so that you can do a handover on layer 2. Yes. But you still need to do handover on layer 3. You still need to do the mobility management on top of it. And for this, you can use mobile IP or whatever, of course. Yeah, there is also, actually, the whole EPS is also available in an proximal IP flavor. Yes, but I didn't want to show it because, yeah. And the second, yeah.
Yeah, just to make sure, the Hotspot 2.0 is currently addressing mobility, but more in a roaming scenario, not connected state mobility, right? The second point is that connected state mobility in Wi-Fi also exists. As Andrea said, it can be layer 2 and in fact is typically implemented in enterprise Wi-Fi implementations. Now, in those cases, there is always a Wi-Fi controller within an enterprise which manages this layer 2 handovers and all that stuff, which is still, to your point, much closer to the edge than it is in the 3GPP case. The last point I want to mention is there is this whole billing issue and the license spectrum. I think it's probably one reason why. And then the wide area mobility. I mean, Wi-Fi mobility, even in an enterprise, is still within a local geographic region. So even if you do want to implement mobility across the nation, I mean, you do need probably to go back into the network. And 3GPP networks are built for that kind of mobility. And then the fact that you're using a licensed spectrum, I mean, makes a lot of difference. I mean, so they want to charge you, so they need to bring your pipes back all the way. In fact, that's one reason why also, I mentioned this LIPA, local IP access and local offload. They're nice solutions, but there is still some reservation for the operators to fully implement it, because of those kind of reasons, not being able to monitor. I mean, that said, the only other thing I do want to say in support of the mobile operator's position is legal interception. Sometimes there is a problem in pushing traffic all the way to the edge, because you do run into legal interception issues, which means that the traffic needs to come back to some legal interception point, which is typically deeper in the network. So.
Yeah. Also, as you said, so one aspect is again this bearer mapping related, or let's say associated QoS profiles, which you get it for free basically, is built in GTP because you have an identifier for this, and it also provides security. So it's encrypted between the eNodeB and the serving gateway. So.
Well, for me, one of the major arguments why I would keep the whole tunneling thing is that you're able essentially to inspect traffic and actually leverage charges on different traffic types.
Yes.
But nobody's doing it. I find it so strange because, I mean, capacity is increasing exponentially, revenues are going like that, and the operators are not piggybacking the costs they have to support the infrastructure onto Google, Skype, Facebook, and all these who make really money out of the infrastructure. And that is a way of doing it, but nobody is doing it. So I find it very absurd, the whole situation. So an operator is paying for the party, and somebody else is enjoying it, essentially.
Absolutely agree.
Because Facebook doesn't have a competition, but O2 has a competition. Operators have a churn problem. If one operator, unless there is they sit together and make a monopoly,
they should.
They have a problem of losing the customer.
Actually, there has been an unprecedented thing here in Spain. Actually, exactly a year ago, Telefonica and Google signed a contract where Google would pay part of the infrastructure, understanding that the users would be happier with a better infrastructure.
Yeah.
I'm not sure it would. Well, it's core network, so it's internet, so it's not the mobile access. But this is like the most expensive part of the whole infrastructure. So, they should essentially pay for the bits they're pumping through.
In UK, there are 5 operators. They are unable to charge exponential, variable rate. They are bound to charge flat rate because of the competition.
Yeah, I'm not saying it should go to the user. It shouldn't go to the user. In fact, we should use it for free.
Yeah, actually, that is a very important point. I mean, they call them the over-the-top services, right? The Google and YouTube and all that, right? So the operator has no knowledge of it. But what is happening, we will have to see the success of it, but in GSMA, there is some effort in trying to, for the mobile operator to work with the over-the-top application providers so that, they can, for example, provide a certain quality of service. So what is needed is that some APIs need to be, or some agreements, business level agreements of course should be there, but beyond that too, there must be some way to detect those flows and then provide that. Because to me, that can be a win-win situation, because if those hooks are in place and the business agreements are in place, then Netflix will prefer to pump their video on a network where there is a agreement, as opposed to a best effort core network. So I believe it is being talked about in GSMA. I don't know exactly what is the status of it. Just the one other point about the mobility part, I do want to mention there is an IETF, a work called Distributed Mobility Management, DMM, where the idea is actually to push the mobility management. Right now it's all anchored sort of deep in the network, even in mobile IP, for example, right? You've got to go all the way to the home agent. So the DMM work basically tries to distribute that anchoring functionality. In fact, we're working with one of the professors from Spain on that project. He's actually I'll get his name, but no, Carlos Bernardo, yeah. Which university is he in? I forgot. Yeah. So he's done a lot of work in this area, and we're actually working.
You need to over-provision the pipes. The data pipes?
No, not necessary. I mean, on demand, right? Say, you're watching Netflix, so at that point it's detected, and it may translate to some billing. You may pay more, or it may be actually absorbed, like you said, between Netflix, the over-the-top providers, and the network operator, network operator. I mean, it can very well be like that.
So, okay, so back to the topic. Sorry, but no problem. Very interesting discussion, actually. Oh, my computer already thinks it's time to sleep here. Okay, so this was basically EPC and EPS. So we remember that EPS comprises, so Evolved Packet System comprises the Evolved Packet Core, which was a large part of that now, and it also comprises the Evolved UTRAN. And so I would like also to give a brief overview of the Evolved UTRAN, but I want to keep it a little bit shorter because I think that you guys actually are more coming from this direction. So, but what are the basic principles? So one basic fundamental principle is actually to have a flat architecture. If you compare to the UMTS architecture and also to the GPRS actually. So you have no radio network controller, which was in the old UMTS architecture basically the point where let's say all MAC related, so the higher MAC stuff did happen, including also scheduling. And you basically all radio related functions are now located in the eNodeB, also including admission control and so on. So you have a kind of distributed radio function admission control, if you want. So another principle is to minimize the signaling towards the EPC, especially for handovers, and that's also one of the reasons why you have an interface between different eNodeBs. Yes. So in the ideal case, if you do a handover, you don't need to involve the MME, the mobility management entity, at all. You just do your handovers. You just contact your target eNodeB and do some information exchange between both entities, and that's it basically. So no additional signaling towards EPC. And the X2 interface, of course, can also be used for handover, neighbor detection, interference coordination. I think you're pretty well aware of that. Then self-organizing networks or SON functions. very important to mitigate the management overhead, because operators don't want to, it's expected that you need more base stations than in the current network, simply because we have to serve more have to serve higher data rates, which automatically means smaller cells. You know this, and the operators don't want to pay for all this management efforts there. So you have some SON functions to reduce these efforts, mainly for stuff like neighbor relations, or which eNodeB is co-located to which other eNodeB, random access channel optimization, PCI selection, so the physical cell identifier, which we know should be orthogonal in the neighborhood, and also mobility parameter optimizations. And we have support for handovers to other radio access technologies like GPS, UMTS, obviously. And for voice is a difficult issue. There are certain different solutions like CS fallback, so circuit switch fallback, where the U is basically pulled out of LTE into, for example, UMTS network to support voice. Another one was single radio voice call continuity. So this is basically if you have an IMS voice, if you have an IMS voice connection already set up, but you don't have any coverage for LTE anymore. And of course, you have also support for Femtocells, which are called home eNodeB. Here, yeah.
Just a quick question. About this X2 interface, does 3GPP specify the scope, spatial scope of this interface? Means one base station eNodeB should be connected to at least, say, 3.
So, no.
No. Means how to decide? For example, for many SON functionalities, this X2 interface is required, but physically there is a need to be connected to some base stations. It can be in mesh topology, it can be in star topology, it can be in is there any detail on that?
So I think the only detail is that an X2 interface may exist, it must not exist, between two eNodeBs, yes. But how do you set up the X2 interface? And that's basically up to
operator.
Up to the operator.
Operator
or the vendor also.
Vendor. Yeah. Because the SON solutions will ultimately depend on the topology connectivity.
Of course.
For example, yeah, if there is no connectivity between, say, all the 6 neighboring base stations,
yeah,
then you cannot kind of design the same SON solution as you could in that scenario.
Yeah.
So there's no specification on that. It's
no. So basically, always 3GPP, let's say, provides a framework to build solutions, but it does not specify only how things are done are normally not specified. The only exception is if it's really required. So in fact, it is required that you do power control in a certain way. Otherwise, the whole system breaks down. But scheduling, for example, you can do it whatever you want. This is not specified.
But for the researchers on SON, this becomes a kind of question where you have to stop and think, okay, what would be the topology, and then you have to tailor your solution.
The topology depends also strongly on on the deployment. So just an overview of what is the evolved U-TRAN. So we have basically it's quite easy. Only the eNodeBs are part of the RAN, of the radio access networks, and we have interfaces, as we learned, between the different eNodeBs, the X2 interface, and also we have interfaces toward the core, in this case toward the MME for user plane data, for mobility management, and towards the serving gateway for user plane data. So, for control plane data towards the MME. So that's S1C, S1 MME, sorry. And user plane data towards the serving gateway that's called S1U. Very intuitive. Then there are different flavors. We have normal eNodeB, macro eNodeBs if you want so. We have home eNodeBs, and since release 10, we have also between home eNodeB an X2 interface. So this was not the case until this release. And we also have now E-UTRAN with relay nodes, basically, where we have here a donor eNodeB and a relay node. The relay node is more or less just a normal eNodeB, which uses the connection to the donor eNodeB as an in-band backhaul, if you want so. And of course, so the EPC entities here are also included because these are important for some of the management functions which are important, which are required in the radio access network. As we can see here, for example, it shows the functional split between the E-UTRAN and the EPC. So, so what you can say as a rule of thumb is that everything directly related to radio aspects is located in the eNodeB. Yes. So that's of course everything here which is relates to the UU interface between the UE and the eNodeB, basically the protocol stack. Of course, that must be at least to some part located in the eNodeB, and here everything is located in the eNodeB. And all these functions which are were formerly allocated in other deeper network entities like RNC, like radio admission control, radio barrier control, intercell radio resource management, and of course the scheduling is also located in the eNodeB. But more interesting, what is not located in the eNodeB. So everything regarding idle state mobility handling is done by the MME. EPS barrier control, as we learned, is done by the MME and the PDN gateway also. And here for mobility, we have the serving gateway, mobility anchoring, UE IP packet address allocation, and packet filtering on the packet gateway. So of course, you know a lot about PHY. Just very brief overview. What is the important aspects here? OFDMA is used. Single carrier FDMA and uplink is used to reduce the peak over average power ratio. And as I said before, we have scalable spectrum use, which is very important. If you want to use some spectra which came free, maybe from TV, analog TV or something like this, so you can scale it here from 1.4 megahertz to 20 megahertz actually, and then you can, again, in later releases of LTE, you can use carrier aggregation to use different bands at the same time, which are located at different frequency. There's a possibility to do localized or distributed resource allocation for either frequency selective or frequency diverse scheduling, depending always on the channel conditions. Lots of support for spatial multiplexing to get more bits per second per hertz. And we have frequency and time division duplex flavors basically for paired and for unpaired spectrum. So LTE TED is primarily developed for the Chinese market. Just a brief overview of the frame structure here for FTD. So we have a frame which is 10 milliseconds long. The frame consists of subframes. Each is 1 millisecond long. Each subframe is again parted in 2 slots of 0.5 milliseconds. And then you have 6 or 7 OFDM symbols per slot, depending on the slot number, basically. And we have the resource grid here, where one resource element basically consists of 1 carrier times 1 OFDM symbol and 1 resource block. It is basically the allocation, the minimum allocation granularity for data. It consists of 12 subcarriers times 1 slot. And here there are also reference symbols included, which are in this case for 2 different antennas. Maybe what's also interesting is that control data is, well, let's say, important control data is normally located in the center of the frequency of the carrier, if you want so, in order to simplify the acquisition of the cell, of the broadcast channel. And in this broadcast channel, there's a master information block, MIP, in each first subframe of a frame. And in this MIP, there's information about, for example, the location of the random access channel in order to get an access to or perform network attachment, information about the cell ID, the global cell ID, and so on. And so this master information block is distributed on 4 frames. So you need the minimum time you need to acquire a signal from LTE is 40 milliseconds because of this then you can basically, you know, aha, there's an eNodeB with this and this information, and then can try to attach to this eNodeB. So just a short overview of the data, or the data path, which is defined between the higher layers and the lower layers. So we have different kind of channel definitions, which have logical channels, transport channels, and physical channels. And I just show here the user plane data, the path of the user plane data through this tree of, I can even say jungle, of different channel definitions. So on the top here we have the downlink transport channel, which is mapped on the downlink shared channel. Yes, logical channel, interestingly. And then it's mapped to the physical downlink shared channel, which is basically more or less the frame structure itself. And on the uplink, it's directly the other way around. We have the physical uplink shared channel, and then again the data transport channel. And we have a lot of different control channel types: paging control channel, broadcast control channel. So this is again for the master information block and system information block, common control channel, and so on. And so how a little bit more detailed view of the protocol stack of LTE. I don't want to go into much detail in the lower areas because you probably know this very well. But on the higher layers, maybe not. So on the top, we have the packet data conversion protocol. And this is responsible for robust header compression. Robust header compression basically is a very important feature for voice over LTE. Because voice traffic has very small packet sizes, which all require an IP header. And this overhead is so large that it's really reducing the capacity if you don't compress this overhead to a significant amount. So this is done by robust header compression, which ensures that the voice capacity of LTE is indeed as large as it was, let's say, advertised towards ITUR. Then we have security functions here for ciphering integrity protection on the control plane. Then we have the radio link control protocol with segmentation of the packets, which are coming from upper layers in different modes. Acknowledge mode means that we have a sliding window, obviously RRQ. Unacknowledged mode is just without any reliability or retransmissions of failed segments. And we also have the transparent mode. And most important here, of course, then below RLC, actually the scheduling takes place. After all this is done, then the data is mapped into the resource frame. So this is something which should not be actually neglected if you think of performance of cellular systems. Yes. So many people just say we calculate bit per second per hertz, but this upper layer stuff can have significant impact on the performance of a system. Okay, so just want to see. Oh, it's a little bit late. I try to speed up a little bit. So, femtocells. So that's basically the reasons why you're all here. And femtocells in CGPP are not existing. So there are no femtocells, if you want. So the term femtocell, I think, does not appear in any official document of the CGP, or at least in a specification. So instead, CGP defines the home eNodeB, in that the home eNodeB is a customer premise equipment that connects a CGP UE, so a mobile phone, over the E-UTRAN wireless air interface, over an LTE air interface, to a mobile operator's network using a broadband IP backhaul, something like DSL or fiber or whatever. Basically means it's a low power, low cost eNodeB with access control. and some kind of secured, hopefully secured transport to the mobile core. In most cases, it's IPsec, I think. And it also uses the same license spectrum as macro eNodeB, so the other eNodeBs as in the network. So, which means it's basically a normal base station, it's just connected via DSL, for example. But the operators or the GPP on behalf of the operators have some large set of requirements on the home eNodeB capabilities. And it's an interesting read if you want to look it up. So first is the operators are more or less in full control of the radio interface of the home eNodeB, which is logically because they are operating a licensed spectrum, yes? So the operator really needs to, they can switch it on, they can switch it off if they want. They are in control of the scheduling, basically, of the power, basically of everything. Also, operators must be able to locate the home eNodeBs to check conformance with regulations, because you can think of a situation where you just take your nice femtocell and go somewhere in another country, for example, from Spain to, I don't know, Russia or whatever. And there are completely different type of spectrum available for LTE in this case. You're simply not allowed to switch your femtocell on there. So this must be, let's say, ensured that this does not happen. Then configuration is, of course, very important, but the configuration efforts should be minimized. So they want to configure, of course, the eNodeB, but as less as possible. Then different modes of access control, open mode, closed mode, or hybrid access mode. Then the UEs should display the CSG type and the home eNodeB name. So if you have your UE, then there should be something like, for example, Misha's home eNodeB, and he then knows, okay, now I can connect to this home eNodeB. Where is he, by the way? Okay. Here. And yes, so then users should be able to scan for available home eNodeBs and manually select to connect to this home eNodeB. And the integrity of the home eNodeB must be validated before communication, which means basically there must be means, some efforts must be taken so that nobody can tinker around and hack the eNodeB and tries to get into the operator's network, which is not very nice. So this is basically, in my opinion, what defines a femtocell in a CGPP network. The requirements on operation and on management. So the architecture looks like this. So 3 minutes? Okay. So basically what's implemented here is we have the normal home eNodeB, which is connected to the EPC with a very normal interfaces, S1MME, S1U, and in between we may have a home eNodeB gateway, which serves as a concentrator for the control signaling here. Yes, to make it a little bit more scalable and easier to handle, basically. We have a security gateway and we have the home eNodeB management system. And we have the X2 interface, but as we know, only since release 10. Then we have different kind of access control. So closed subscriber group basically means that only MEM or UEs which are part of a certain list, which of this group basically are allowed to access a UE. And this basically can be enforced with different lists. One is allowed CSG list, ACL, which is maintained by the user, for example, via web interface. And the other one is the operator CSG list, OCL, which is pre-provisions list of the operator. And the CSG ID, so each of the CSG group has an ID, is broadcasted by the home eNodeB. So this is a way how the UE actually is aware of whether it belongs to this CSG or not. This would be an example of mobility and would also explain how PCI confusion is solved. We heard this before. I think I will just talk about it. Because it's quite interesting. It's a new feature in release 10. So this is a mobility example from the eNodeB to the home eNodeB, yes? And what happens first is the source eNodeB tells the UE you could report proximity towards an eNodeB, a home eNodeB which is known. So this is proximity indication. The UE reports this proximity indication to the source eNodeB if the source eNodeB, if the target eNodeB is in CSG whitelist. Then the source eNodeB tells, do a reconfiguration, do a measurement basically of the physical cell identifier. Yeah. The problem is the PCI. There are not so many PCIs. There are 504 PCIs in total in the system defined. So it could very well happen that there are many home eNodeBs with the same PCI in the same coverage area of a target eNodeB. So there's a confusion because the target eNodeB does not know to which home eNodeB should it connect them. So is it solved in a very pragmatic way? Because the UE gets the command to scan for the system information, so for the master information block from the target eNodeB. This takes some time, as we know, at least 40 milliseconds, and also it's a little bit power consuming. But after this, it gets the cell global identifier, which uniquely identifies the cell, and it gets some additional information, the checking area ID and the CSG ID and so on. And then the UE can report this information back to the source eNodeB. The source eNodeB in this case knows, aha, I have to connect to this home eNodeB, but not to the other home eNodeB. That's basically how the PCI confusion is solved in release 10. It probably has some more room for optimization. Okay, how many minutes do we have? We have maybe 2 more slides. Okay, let's say interference coordination, of course, is also a very important point. And there are currently 2 approaches discussed in 3GPP. And one is interference avoidance based on carrier aggregation, which basically means that in case that you have at least 2 carriers, here indicated by F1, F2, for both macro and femtocells. You can schedule your control information on orthogonal carriers, so one here, so not subcarriers, carriers, yes, in order to avoid any kind of control channel interference between these 2 layers of the network, because that's the main problem, control channel interference, because you cannot schedule control channel information out of the way, yes, between different network layers. And what you can then do is you can do either just use these different layers, or you can also do cross carrier scheduling if you want so. So you can say here, I want to schedule my data now into this carrier which is normally used by the macro cell, or the other way around. But this is an approach that is more likely used for pico or for small cells. For femtocells, it's a little bit unclear whether this will be used. And for this, we have another approach, which is time division multiplexing, basically with almost blank subframes. It's a very nice term. I like it. Because what basically means is that subframes are muted out. So there is no information sent on certain subframes, I think in all cases in the femto side, so that the UE can still hear the macro cell, yes? But it cannot be completely muted out. You still need to send some control information. For example, the common reference symbol, synchronization reference symbols, and so on. And that's the reason why it is called almost blank subframes. The problem here is, of course, that you lose capacity here because you cannot schedule anything here. Also, you have high degree of variation in interference during this time. So this is normally not very nice for the overall stability of the network. And we will skip all this and come just to the end, where we'll show some hot topics which I think will become very important, or are already important in the very near future. One is, of course, the whole topic of heterogeneous networks. So we have seen there's a lot to do there. Mobility enhancement. If you think you're moving around an area where many small cells, large cells on top of each other, so you can do handover optimization according to your speed, according to the traffic type, and so on. So there's a lot of room for improvement there. And also, of course, for intercell interference coordination. I think now after enhanced interference coordination, so EICIC, we even have now further enhanced interference coordination as a work item in I think for release 12 of LTE. Then we have carrier aggregation, which basically means that we want to use simultaneously several component carriers at the same time. So we have nice flexibility for also not only in terms of bandwidth in total, but also in the ratio, for example, for the uplink and for the downlink carriers. You can think of something like you have 2 times 20 megahertz carrier in the downlink, and we have 1 times 10 megahertz carrier in the uplink. The only problem may be something related to regulation in this case. But there are some challenges for synchronization, because if the carriers are on different frequencies, you have a different time advance values, basically, yes. So this is something which still has to be solved. And also for MAC controls like random access channel, where is which information is scheduled when. Then we have optimizations or enhancements for machine type communication. So as you know, machine-to-machine traffic becomes very important, because M2M means you have a huge number of devices which only sends a small number of data. And the whole system is not optimized for this kind of traffic, because you need to set up, which we have seen, you need to set up all the bearers, you need to do all the state management in the core and so on. And this is something which is not efficient for this small data volume. So there is a lot of work and efforts going on in this direction. Then also user plane congestion control, because we have seen on real life examples that operators have a lot of problems with in congested scenarios right now. And this will not go away in the future just because we have maybe a little bit better, or maybe even a lot better radio access network. We still will have congestion in the network. And this is something which has to be solved rather quick, I would say. And of course, also an always good topic is coordinated multi-point transmissions, which was promised actually to be already part of release number 10, but got postponed and postponed because it's a rather complex topic. But it's still, of course, on the work item list of CGPP. And that's it from my side. So I have some information about important links and documents here. And yeah, that's it from my side. Thank you for your attention.
I think we had a good discussion during your talk, Andreas. Really.
Yes.
Are there any other questions burning up in the audience? You? No. One last one.
Yeah, last one.
Your question counter is on 0.
Just simple question: why LTE restricted to PCI to be just 400 or something?
Yeah, that's a good question. I think it has to do with the, first of all, is there an expert in the audience which can answer this question? Maybe
because I see that because of this limitation, they are going through a lot of trouble in addressing, and
yes.
The addressing process is very complicated.
So I understood it's a,
even for macro cells.
I understand it's a orthogonal sequence, which is basically, so the PCI is coded with an orthogonal sequence, and the orthogonal sequence has a certain length, and this length restricts the values to 504
yeah, but
items.
We could have more longer. By just increasing 1 bit, we could go to 1,000.
Probably, but I'm not such a DeFi expert. It's a design selection choose basically.
Okay, then let us thank Andreas again for the fantastic overview.
Thanks.
And I hope to see you back tomorrow, 9 o'clock, for our second day, which is a little bit more fire-oriented. Very quickly, logistically, if anybody needs a taxi and there's nobody at the reception, just come to see me. I'll get you a taxi. And if you go out in Barcelona, just mind the pickpockets. Hotels are safe, so you can leave your documents there, but the pickpockets, please mind them very carefully here in Barcelona. All right, thank you very much.